Let's talk about homework problem number 8. In this problem, there's a toy gun that has a spring that launches a little ball out of the gun. And we're shooting vertically. We're launching this ball in the vertical direction. So this problem is kind of interesting because it involves both spring potential energy and gravitational potential energy. So let's see how it's set up. There are two parts to the problem. In the first part, we have the spring compressed with the ball on it, and then the spring launches the ball up to a maximum height above this zero level. Now the zero level is the equilibrium height of the spring. So that's when the spring has zero compression. The problem tells us the height, the problem tells us this initial compression, the problem tells us the mass of the little projectile. And so our job in part A is to figure out the spring constant, figure out the value of K. So I drew a sketch of the initial and final situations that we'll consider when we do conservation of energy. So let's write down the conservation of energy equation now. Initial energy equals final energy. We need to keep track of all the different types of energy in the problem now, because we have gravitational, spring, and kinetic. There's our initial gravitational potential energy, our initial spring potential energy, our initial kinetic energy, and then we have the same stuff on the right. Final gravitational potential energy, final spring potential energy, and final kinetic energy. So this equation looks kind of like a mess because there's 6 terms in it. Fortunately, a lot of the stuff is 0. Let's think about what's 0. The object starts from rest at the beginning, so there's no kinetic energy. And at the end, the spring is no longer compressed, so the delta x in the final situation is 0. So that spring potential energy goes away. And when the projectile reaches its maximum height, as we've learned in kinematics, that means its speed, or at least the y component of its velocity, is 0. It's only moving vertically, so there is no x component. So that total speed is 0. So in fact, half of those terms go away, and our equation is easier to deal with. So let's do some algebra and start solving for K. We've got 1/2 K times delta x initial squared equals mgy final minus mgy initial. Let me simplify this right-hand side a little bit. And last step, K equals 2 mg y final minus y initial over delta x initial squared. Now there's one slightly tricky thing in this formula. and that has to do with y initial. The initial height, well, first of all, in gravitational potential energy, you can define zero to be wherever you want. So let's define zero height as being this equilibrium height of the spring. So let's say that this height is also y equals 0. Not only is it the equilibrium position of the spring, but let's also call it the zero height for gravitational potential energy. So that means that we started out below. So that's going to be negative x initial in here. So there'll be two negative signs. So now we can finally write the full answer. 2mg y final, which I called h, that height, and that number is given to you in the problem. And y initial is negative delta x initial. So there's two negative signs. So we can just add that compression of the spring there. That's a number given to you in the problem. And we divide by delta x initial squared. Right, that's the spring constant. And let's tackle the second part of the problem. It says, let's figure out the speed that the projectile leaves the spring at. So when you launch this thing, how fast is the projectile moving? Now there's two ways you could do this. I addressed this in another video I posted this week about how do you decide what's the initial and final situation. To answer part B, you could do it using these two pictures like I already drew. Or if you wanted to, you could analyze it using this picture and this one. It doesn't matter which two you use because the total amount of energy is always the same no matter what. But I'll stick with these two. And again, we'll write our conservation of energy equation. And as before, we have a whole bunch of stuff. Unfortunately, this time, not as many things are going to be zero. Actually, I misspoke. I think we'll still have the same amount of zero quantities as before. Let's see what's zero. Gravitational potential energy, that's not zero, because y initial is going to be negative delta x initial. Initial spring potential energy, that's not zero, because this thing is not zero. Initial kinetic energy is zero. That projectile's at rest. Final gravitational potential energy, well, here's the final scenario, and remember we also were considering this height to be zero, so y final is zero. And the spring is not compressed at the end, so the spring potential energy is also zero. And there's the final kinetic energy. We're trying to solve for the V final here. It's the V in this picture on the right. So that's our variable that we need to isolate. Let's do some algebra. We don't have to do a lot of algebra. In fact, we can do this in just one step. We'll multiply by 2 over m, or divide by 1/2 m. So we have 2 g y initial plus k over m delta x initial squared, and all of that gets square rooted. Now, if you want to double check your answer, you could try doing this problem using this picture and this one, and you'll get the same value for V.